Hi everyone, here's a video going through problem 7 off the homework set for 12.1. It's based on problem 27 out of the book. Um, so the setup here is they give us this data table where they have observed these regions where rockets may have fallen, and they're giving us the number of regions that they observed for each count of rockets that may have landed in that region. So 0 through 7 are the possible values for the number of rocket hits, and the second row is the number of observations of each of those 8 options. So the first part asks us to estimate the mean number of rocket hits by computing this number. So this looks like a probability distribution. This is the expected value. What I've done is I've gone ahead and done this in Excel. The computation's not so bad that you couldn't do it by hand, but Excel just gives me a convenient way to put it into a table. Of course, you could do StatCrunch, but the formulas are a little bit more cumbersome there. So you could use a hand calculator and then type them into StatCrunch if that helps. So I'll work through this whole thing as we go, but the data set that we're given is here. What I've done down here is just add up the total number of observations. So we know there are 566 regions, so those are observations. And I needed to compute the probability of x in order to compute this formula. Well, the x is the number of hits, so that's the variable in question, and b is essentially the frequency, the number of times we've observed that value of x. We need to convert that to a probability, so all that means is take the number of times and divide by the total number of observations. So in each case, I've just gone ahead and done that. B2 divided by 566, and then the next one, of course, B3 divided by 566. So all of these give me the P of x's that I need for this formula. Just to check, I went ahead and did the sum of this row, and I should get 1, and I do get 1. So now in column D, I'm just going to do, and I'll show you how I actually do this, x value times the probability of that value. And the nice thing about Excel is what you can do is drag that down, and the formula repeats the way it should. And then down here, what I did is took the sum of those values, and that is what this formula is asking for. X times P of x for all possible value of x. Add those up. That's mu. That's your mean value. And they want us to round to 4 decimal places, so that's where I got 0.9470. That's that value. We'll be using that value throughout. Part B says you can't use the goodness of fit test with the data as it comes to us, and the reason is that the values are actually too low. So you don't have expected counts that are bigger than 1. Now these of course are observed counts, but with observed counts of 0, you can see that that's pretty low values, and that's why I've checked this value C, and then this this option D as well, because 1, 2, 3 out of 8 are probably going to be less than 5, and so that's why as is you can't do a goodness of fit. Part C is asking us to, what they're trying to do is see if the Poisson probability model is a good model for this. So we're leading up to a hypothesis test to see if this model fits the observations well. So this is the formula for Poisson. You don't have to memorize this, but what I've done is for each value of x, I just went ahead and computed this. Mu is the expected value we computed in part A, and then x runs through all the values, 0 through 7, and e is the exponential, natural exponential base. So what I've done here is made a new column. I called it Poisson because I already had used P. And I went ahead and typed this formula in. 0.947, that's mu to the power, see if I can make this a little bit bigger. 0.947, that's mu to the power of x, remember x is in column A, divided by x factorial, that's coming from the formula, so that's a fact of the argument in Excel. Again, you can do this on the hand calculator, it'd be fine. And then exponential is the natural base to the negative mu. And so I do this for each of these values, and you'll notice in this case they've asked us to consolidate the last four categorical options here, the 4, 5, 6, 7. So if you add up the values of 4 or more, that occurred in 8 regions. That's where they got the 8. And what we can do here is I use that Poisson formula for 0, 1, 2, 3, and then to find 4 or more, you can just do 1 minus the sum of the previous. So this whole thing has to add up to 1, so if you've calculated 4 out of 5 rows, then the 5th row should just be 1 minus the sum of the other 4 rows. And that's where we got these values here. And so what I've done back on the problem is gone ahead and typed them in to 4 decimal places. So you'll see for x equals 0, 0.3879, I'm getting that from that value. And then all the way to 4 or more, 0.0159, I'm getting that from that value. So now we've set this thing up. Like I said, we're headed toward a goodness of fit test, so they're asking us to use that Poisson probability distribution to calculate the expected number of hits, or expected number of observations for each number of hits. And so we do that by, okay, so now we have a probability in each category. To get the expected value, we take, well, the total number of observations is 566 times that probability. So in each case, what I'm doing is taking 566 times the corresponding probability, and I'm getting these expected values for each of the new 5 new categories. And that's from typing in here. They tell us round to 2 decimal places. So 219.55, that's the first one, all the way down to 9.00, that's the last one. And now we're actually going to go through in Part E and conduct the goodness of fit test. If you'll notice, these expected values, because they lumped the last few categories that had the lowest number of observations into a single category, now these 2 conditions that failed in the expanded version don't fail in the modified version, so we can actually do a goodness of fit test. And so they make that note for us. The goodness of fit, null, and alternative hypothesis are always the same. Basically, the null hypothesis is that whatever model you're considering models the situation well. And so that's why H0 is the rocket strikes can be modeled by a Poisson random variable. The alternative hypothesis is that they can't be modeled by a Poisson random variable. In other words, the model doesn't fit. So here's where I'm going to go back to StatCrunch because it makes these computations really fast and easy. So in StatCrunch, what you'll need, I'm here in Excel, I'm going to need observed, and I'm going to need expected. And remember, we changed this to an 8 because we've consolidated the last 4 rows. So over in StatCrunch, I have that here. I think I went ahead and copied the whole Excel table here, but really what I need is the observed number. Notice I changed that 7 to an 8, and this should really be 4 or more. You can do a 4 plus or whatever, but that's just a category. Oops. See if I can, that should have been 8, sorry, typos. So this is 4 or more, but this is just a label. So what you do to do this goodness of fit is go to Stat, goodness of fit. We're doing a chi-square goodness of fit test. The observed is the data that came to us from the table, from the problem, and the expected is the one that I labeled expected over there in Excel. And that's it. You click compute and you get this value. And so it's giving you the chi-square value, it's giving you the p-value. So I go ahead and put those in. The chi-square value rounded to 3 decimal places, 0.816, the next digit is 2. And then the p-value rounded to 4 decimal places, 0.9363. And so that gives us what we need in order to state the conclusion of the hypothesis test, which is, well, with a p-value that high, let's see, they told us the alpha value should be 0.05, which is typical. 0.01, 0.05, 0.1, that depends on the context. Either way, a p-value of 0.9 is huge, so it's not smaller than the alpha level. In other words, this observation fails to meet the burden of proof needed to reject the null hypothesis. So our conclusion would be we do not reject the null hypothesis. There is not sufficient evidence to reject the claim that the rocket strikes can be modeled by the Poisson random variable. In other words, this observation did not marshal adequate evidence to side with the alternative hypothesis by rejecting the null hypothesis. We did not meet those conditions, and so that's why we do not reject H0. And that should be it.